My name is Chris Wirth. I'm a faculty member in the Department of Chemical and Biomolecular Engineering here at Case Western Reserve University. I'm a chemical engineer, so all my degrees are in chemical engineering. I did my undergraduate degree at the University of Buffalo, near my hometown, Buffalo, New York. And then I went on and did a PhD in chemical engineering at Carnegie Mellon University in Pittsburgh. I then spent a little bit of time in industry, PPG, which is a coatings company in Pittsburgh. And then I went and did a postdoc in Belgium at a university called KU Leuven. And then I relocated back to Cleveland around 2014 and started on the faculty down the street at Cleveland State University. And then last year I moved to my current position at Case Western Reserve. So all of my work, all of my training has been in the area of colloid science, interfacial science, complex fluids. And one of my passions is really sharing with other people how relevant this type of work is to our everyday lives, because it's an area that's not typically covered in high school curriculum, and it's rarely covered in college. Usually it's just, one section in your intro chemistry book, but actually colloids, complex fluids are very, very relevant to our everyday lives. In fact, I can pretty much guarantee that you've used a colloidal material so far today. So what I'm going to do in the next 25 minutes or so is basically show you a couple cool things about our lab, what we do. I can answer any questions. This is obviously a new experience for me to run this kind of webinar. Usually I have this type of interaction in person, but there's nobody else in the lab today. So it's just me talking to a webcam. So feel free to ask questions. I'm gonna just check the Q&A here. Oh, there is a chat. Let's see what the chat is. Okay, so I think a couple people realized that I was muted, and I think I'm not muted anymore, which is good. But let me know if you're still having audio issues. Okay, so why don't we get started? So I guess the first thing I want to do is just kind of give you a tour of my lab. So I'll try to do this in an efficient manner. So this is the laboratory. It essentially consists of one large room. That large room has a couple bays where we have experimental setups. And then there's a little bit of a kind of an office area here. Most of my students actually have offices in another room, but this is just an area where they can set up and work. And as we move along here, you'll see a couple of vent hoods. One of the major kind of tools in our lab is that of microscopy. Okay, so we have a couple microscopes, some of which are kind of more off-the-shelf microscopes, and some are custom. So this is one of the off-the-shelf microscopes that we have. It's an inverted microscope, which means that you look at the sample from underneath. So I'm unsure kind of what levels all of our attendees are at, but basically in microscopy, you either look from above at a sample or you look from below at a sample. And this is one of the microscopes that you look at sample from below. We also build custom setups. This is one custom setup here that you can see here. Most of the components are off-the-shelf components that we put together in ways that are helpful for our projects. This particular microscope is utilized for a project on coatings, drying thin films, that's funded by the National Science Foundation and in collaboration with PPG. So those are a couple major tools in our lab. We also have another room in our laboratory. So it's a little bit loud, but this is actually a clean room. So the circulation of air through this room is regulated to minimize the amount of dust that appears. And again, we have a couple microscopes here. This is an inspection microscope. It's a microscope that allows you to have very few things underneath and allows you to look at samples that might be kind of unique or large in size. And then the last microscope at the end there that's what's called an upright microscope. And the upright microscope, you look at samples from above. Okay, so let's go back to where we started. Okay. So I'm just going to move the computer here so I can answer any questions there might be. Okay. All right. So the first thing, let me get this a little bit closer, that I want to do is just give you a little bit of an introduction to what colloids and complex fluids are. Okay. So you can see on my title slide here, I have this video. This is what's called a complex fluid. It's actually a shear thickening fluid that I'll show you some more examples of. But you can see that even though it flows in a weird way. And the reason why it flows in that weird way, actually I'm going to do this. And the reason why it flows in that weird way is because the relationship between the way it strains and the stress that you apply is what's called nonlinear. So lots of fluids that you interact with on a daily basis, like shampoo, especially shampoos and creams, lots of foods have this kind of weird behavior, which differs from the behavior that you would see in, like, for example, water, which would be called, a Newtonian fluid. So the first thing I want to do is just kind of emphasize again how common colloids and complex fluids are. So colloids and complex fluids are found in many products that you use on an everyday basis. So lots of consumer products like shampoos and creams, things that you would utilize in the bathroom for personal care are many times colloids and complex fluids. One of the kind of things that got me initially interested in this area was looking at the ingredients on the back of a shampoo bottle. So if you look at the ingredients on the back of your shampoo bottle, you'll see lots of components that have the name of, like, sodium dodecyl or sodium laurate sulfate, for example. And these ingredients are what are called surfactants. And surfactants help with detergency. So surfactants are found in shampoos, obviously, but also other soaps and detergents. And surfactants form micelles and would be considered colloids in this context. So colloids and complex fluids are found in consumer products. Are also found in food. So I have a couple pictures on my slide there that you should see of foam, the foam head on top of a beer. This would also be considered a colloid. Also mayonnaise and milk. These are both colloids. Also chocolate, which is another food, is a colloid. And the interesting thing about chocolate, which is similar to other food like ice cream, for example, and yogurt, is that the way that you process the material in the microstructure that forms in that material affects the palatability of that material. So, for example, chocolates are made by tempering. That's where you have a controlled heating and cooling process for the fluidic chocolate. And that tempering process is designed to produce particular sizes of domains of microstructure in the product, which leads to different levels of palatability in the product. Okay, so that's one of the reasons why chocolates can taste differently. Taste different is because of the way that they're tempered, and then as a consequence, the microstructure that forms in that product. Also, blood is a colloid. So blood consists of fluid with lots of suspended material, And that also can have really kind of interesting behavior. And actually, we have a merging project now on blood in our lab. Okay, so colloids are everywhere. I mentioned this, but the thing that really makes colloidal and complex fluids important and interesting and fun to study is that they have something called microstructure. Okay, so they have structure that forms as a consequence of a variety of forces that might occur on the molecular or a little bit larger scale that gives you a structure on the micro scale that's very potentially useful and interesting. And in fact, that's why we have so many microscopes in our lab, is because we use microscopes to observe a lot of this behavior. So you form a colloid, and this is probably something that if there's any high schoolers in the crowd, you might have seen in some of your chemistry textbooks. A colloid is formed by essentially taking two immiscible materials and processing them in a way where one of the materials is finely divided in a second material. Okay, so the classic combination of these I have shown on my slide here, where you take a solid and a liquid, for example, that would be a suspension. You might take, what else is on there? Two liquids, that's an emulsion. So like, for example, mayonnaise is an emulsion where you have water and oil, or oil and water. And then, liquid dispersed in a gas, this would be considered a foam, for example. For example, you had gas dispersed in liquid, or vice versa. So that's how you form these materials. And the main thing that makes a colloid is that one of the materials is finely divided in this other material. Okay, and by finely divided, we mean that the first material that's dispersed in the second material is between a nanoscale to a micrometer in size. So this is really, these are really nanomaterials in the sense that the things that kind of make it a colloid are on the size scale of a nanometer to a micron. Okay, so let's get into something pretty fun. So what I want to show you first, so I'm going to basically show you two things. I want to show you some high-speed photography of a shear thickening fluid. And then I want to show you some videos from another project where we have particles swimming around on their own. Okay, so what I've prepared here is something that you might have heard of before. It's Oobleck. So, for example, Mythbusters have done a part of their show on Oobleck. But Oobleck is a shear thickening fluid, and you can make shear thickening fluids a lot of different ways. But the way that you make Oobleck is by mixing cornstarch and water. And there's different recipes that you can utilize, but I usually use about 2 parts cornstarch to 1 part water. And if you do that, and I wish you were here, because if you were here, you'd be able to touch this, but maybe next year. Let me just put on my gloves here. You get a fluid that looks like this. Okay, so it looks fluidic. If I move it around, it jiggles, right? And what I can do is, so what I have here is another container with Oobleck. Okay. And I can pour it from one container to the next. So I can pour it. There's a little bit of a watery part, but you can see that it flows just kind of like a liquid. Okay, and the way it flows will depend upon the concentration of cornstarch that you use. So if you use more cornstarch, then it'll shear thicken a little bit more strongly than if you use less cornstarch. But nevertheless, it flows like a liquid. Okay, but you can see if I press down on it, It's not splashing, right? It's not, I mean, there's very little bounce back. It's not as if I'm sticking my finger into a little jar of water, right? And I'm hitting it pretty hard, okay, just like this. And you can see that there's, you know, it's kind of behaving more like a solid, okay? And the reason why there's that response is inherent to the fact that it's a shear thickening fluid, okay? So shear thickening fluid, as you might imagine from its title, or its name, is that when you shear something very hard, then its viscosity actually increases dramatically. It hardens to the extent that it almost feels like a solid, okay? So the harder you shear it, the harder it becomes, which of course, for certain applications might be really useful. So for example, bulletproof vests. If you hit something with a hard impact, it'll feel as if it's a solid, but at rest or under very, very weak shears, then it flows like a liquid, okay? And there's some interesting there's some interesting things that you can do with this fluid that are pretty fun. So here I'm gonna just, first I'm gonna kind of set up what I'm showing here. So I think you can see it on the video. It's right at the bottom here. I'll back this up a little bit so you can see better. Okay, so here I have a high-speed camera, okay? And that high-speed camera was utilized to take some video of a tennis ball hitting the surface. Okay, so a tennis ball will bounce when it hits a solid surface. But of course, if you threw a tennis ball at a pond or a bucket of water, you wouldn't expect it to really bounce much, even you know, maybe it doesn't even bounce at all. Okay, so I took this tennis ball and I bounced the tennis ball against first a solid surface, and that's the video that I've shown here. Okay, and you can see that it bounces back just as if you would expect. And you know, a few notes on this high-speed photography. So I'm capturing these images at something like, you know, between 4,000 and 6,000 frames per second. That's why I'm able to get these beautiful videos. We do also use this camera for research, where we actually hook up the camera to the microscope and visualize microscale phenomena that happen in just a fraction of a second. And this type of camera allows us to capture some of these phenomena. So that's a tennis ball bouncing on a solid surface. And you know, you might expect if I was to throw the tennis ball at a fluid that it would either bounce very little bit or it would sink into the fluid. But indeed, if you throw the tennis ball at the shear thickening fluid, then it bounces right back as if it has hit a solid, okay? And you'll see actually there is some evidence that this is a fluid because you see some deformation, but nowhere near the deformation or the splash that you would expect to see if the tennis ball was to hit a little you know, puddle of water or a jar of water. And of course, the reason why this happens is that I'm throwing the tennis ball very hard at these objects, and the tennis ball is impacting this shear thickening fluid to the extent that the shear rate is very, very high. And as a result, the fluid responds as if it's a solid, okay? So this is just kind of one cool example of what you can do with a shear thickening fluid, which I think is really fun. And there's been some applications of these fluids in real life that, you know, I encourage you to look into. The last thing I want to show you is just to prove again that this is indeed a fluid. So what I've done here is I've taken a couple nuts and bolts and I've dropped them from up here into the fluid. And you'll see actually initially the nut will bounce off just a little bit, but then once it falls back into the fluid, it rests very gently. Okay, so you can think of the initial impact of this nut to be a very high shear rate, and then once it falls onto the fluid, it's just under the influence of gravity, which is a very, very low shear rate or weaker shear rate. And as a consequence, just sinks into the liquid as if it's a fluid. Okay, so you can see it initially impacted, it bounced a little bit, and now it sinks into the fluid. It sinks into the Oobleck as if it's behaving like a fluid. Okay. So I'm going to just check the chat real quick. Just make sure that there's, let's see. Okay, cool. All right. So in the last few minutes, what I want to do is show you some videos from another project that we have. So I'm actually going to move into our other room. Okay, so this is where we do a set of experiments that are on what are called active particles. Okay, so the video that you see on my screen are microscale particles. These are a fraction the size of a human hair that have been designed chemically so that they swim around on their own. And we do these experiments with a microscope because a human eye wouldn't be able to observe these things without it. So you can see the particles swimming around just like this. And you might think of kind of these interesting dynamics as if it's kind of like a colloidal square dance, where the particles initially interact and then they dance around and go on their separate ways. And this is actually a really useful synthetic system for studying biological phenomena, because some of the things that we see in these active particles are things that we see in swarms of bees or flocks of birds or schools of fish. Okay, and in fact, these particular active particles are great analogs even for microorganisms, and that's our interest, is that we want to learn more about how microorganisms swim. So we design and fabricate these active particles so that we have a synthetic system to study with our microscope in a controlled environment in our laboratory. Okay, so that's, and this project, I should say, was initiated by a current PhD student in our lab, Marola Isa, who wishes she could be here, but she's in class right now, so she can't make it. But if you have any questions, I can forward that information to her. So we're just about out of time. And what I want to do now is just answer any questions that you might have and kind of finish up. Okay. And what I'll do is I'll just put my main slide here so that you can see my contact information in case you want to get in touch with me via email. You can check out my website, or you can connect with me on social media, on Twitter. And I also like to thank the National Science Foundation. So all of the work that we do in the area of colloids, complex fluids, was made possible by the National Science Foundation, and a lot of these outreach activities that we do were made possible by NSF. So just want to thank them and look, let's see, we got a question, I think. How do they swim around on their own? That's a great question. So these particles are, they're microscale spheres, and the particle themselves is made of a polystyrene material. And then on one half of that polystyrene bead, the particle is coated with platinum. Okay, so these are called Janus particles, and if you Google active Janus particle, you'll find quite a bit of material. And we put these Janus particles into a solution of hydrogen peroxide. The hydrogen peroxide then reacts with the platinum and decomposes into oxygen and water. And this reaction is actually what creates the chemical environment around the particle that allows them to swim on their own. Okay, so this is one mechanism by which you can make these microscale particles swim on their own. There's a couple other, but the one that we use is really kind of like the most popular. And again, if you have any questions or anything, I would be happy to talk more about it, you know, via email or offline. Let's see. Okay. All right. So, you know, my final message is essentially that, you know, colloids are everywhere, complex fluids are everywhere, and chemical engineers can work in this area. I know I have lots of collaborators and colleagues that work in advanced materials and coatings, in food, for example. So there's lots of areas that you can get into working in colloidal materials. And again, if you want to learn more about it, just you can get in touch with me. All right, so I hope everybody has a great day and you enjoy more of these Engineer Week activities hosted by Case Western. I think this is a great event, and hopefully, you know, next year I look forward to seeing you in person.